Hello everyone and welcome to the coronavirus edition of the fourth exercise from our signal theory class. In the first part of this exercise we will practice filtering in the spectral domain. We will do this in MATLAB, and at first we will practice on an artificial signal, so-called chirp signal, and then we will move on to ECG. What is a chirp signal? That is essentially just a sine wave that increases its frequency over time. How do we generate a chirp signal? Well, we can do it like this. We will start by setting our sampling frequency to 1 kHz. And from there I will get my sampling period. Now I will set that my signal will be half a second long. And now I will generate the vector of time. And you can see that the vector of time goes from 0 with step of sampling period all the way to that half a second. Now if I wanted to generate a constant frequency sine wave, I would do it like this. And I would set that my frequency is something like 200 Hz. But I do not want to generate a constant frequency sine wave. I want my frequency to be rising with time. So I need to make my frequency proportional to time. And this will be the constant of proportionality. If you set it like this, your frequency will go from 0 to half the sampling frequency in this time. Let's take a look at it. And here we go, this is the chirp signal. You can see that it is a sine wave that starts at very low frequency and then the frequency is increasing. Now a chirp signal is very convenient for practicing of filtering because it contains all of these frequencies from lowest to highest. So now I will try to implement filtering in the spectral domain. Specifically, I will try to implement a low-pass filter that will keep low frequencies and suppress high frequencies. I will try to implement a low-pass filter that will keep frequencies from 0 to 200 Hz, and then it will suppress frequencies which are above 200 Hz. Okay, let's do that. If I want to do filtering in the spectral domain, I will need to take my game into the spectral domain. So I will need to take the discrete Fourier transform of my signal. And remember, this FFT stands for fast Fourier transform, which is just computationally efficient implementation of the discrete Fourier transform. Now that I have my spectrum computed, let's plot it. I will try to keep everything in a single figure, so I will use subplots. Remember, you need to plot the magnitude spectrum, the absolute value of these complex numbers. If you don't, you are going to end up with complex numbers and those are going to be difficult to look at. Before I run this, I will label my axis. There it is, now I can run it. And this is my result. So what I have here is the chirp signal in the time domain. On the horizontal axis I have my indices, my time indices, and this is the discrete Fourier transform spectrum of my chirp signal. On the horizontal axis I have those discrete Fourier transform indices k. Now remember, MATLAB gives me one period of the discrete Fourier transform spectrum with length which is equal to the length of the signal. And this horizontal axis corresponds to the frequency axis from 0 to the sampling frequency. Further, remember and observe that this part of the spectrum is just a mirror image of this part of the spectrum. Now what do I want to do? I want to implement a low pass filter that will keep some low frequencies and suppress those high frequencies. So I need to keep these low frequencies and I need to suppress these high frequencies. And of course I need to do it symmetrically here. To do this, I will need to define my frequency characteristic. And remember from the lecture, my frequency characteristic will have to look like this. This is the frequency characteristic for a low pass filter. So in MATLAB, I will be working with this one period of the DFT spectrum, and these indices, which I will set to 1, will indicate the frequencies that I will pass, and these indices that I will set to 0 will indicate the frequencies that I will suppress. And of course, I will need to keep the symmetry. Now the trick is to know which are the exact indices that I need to set to 1 and which are the exact indices that I need to set to 0. This frequency axis is not in hertz. This is just these are just numbers 1, 2, 3, 4, 5. So I need to recompute my frequency in hertz to these indices. And how do I do that? Well, I need to recall what we talked about on the last lecture and exercise about the correspondence of the frequency axis. Naturally, we use this frequency axis where we have frequency in hertz, but if we sample our signal with sampling frequency of fs, then to analyze our signal we will have to use the discrete time Fourier transform, and we will end up with normalized frequency, where the sampling frequency always corresponds to 2 pi, and half the sampling frequency always corresponds to pi. But if we do something in MATLAB, we will have to use discrete Fourier transform, and we are going to end up with this frequency axis. Here we will just have unitless index k, and the sampling frequency will correspond to this uppercase N, which is equal to the length of our signal. So if I know my frequency in hertz, how do I find out which index of the DFT transform corresponds to this frequency? Well, this is quite easy. I can just use proportionality. I can write that this frequency divided by the sampling frequency must be the same as this k divided by this uppercase N. And that is what I have written here. The frequency in hertz divided by the sampling frequency is equal to index k divided by uppercase N. And from here I can get that index k is frequency in hertz divided by the sampling frequency times that uppercase N, which is the length of the signal. So let's use this. I have said that I want to generate a low pass filter that will pass everything from 0 to 200 Hertz. So by using this formula, I can compute which index of the DFT transform corresponds to this frequency. And I need to set that the capital N is the length of my signal. And by doing this, I have computed the index which corresponds to this line. Well, almost. If I run this code and I take a look what my k is, I will find out that my k is not integer. And this is a problem. The k has to be an integer, so we need to round it. And now I have actually found the index that corresponds to this line. Using this, I can now generate my frequency characteristic. At first I will generate it as zeros, and then I will set these lines to 1 and these lines to 1. Now I have generated those zeros, and now I will set that the frequency characteristic from 0 to k is 1. And now I need to take care of these lines. Remember the symmetry. If I do something to the first line, I need to do the symmetric operation to the n minus first line. If I do something to the second line, I need to do some symmetric operation to the n minus second line. If I do something to the case line, the corresponding line is n minus k. So I need to set my frequency characteristic to be 1 from n minus k to the end of the spectrum. At least the spectrum that is right now in MATLAB. Okay, those of you who know MATLAB may be slightly nervous because you can see that I'm using 0 for indexing here, and that is just not going to work in MATLAB. In mathematics, we do use indexing from 0, but MATLAB has this shifted. MATLAB is indexing from 1. So all those indices that I have computed, I need to shift because of MATLAB. So I need to add one here, and here, and here. And now I have proper symmetry in MATLAB. I have generated the frequency characteristic, so now we can plot it. I actually do not have to plot the absolute value of the frequency characteristic in this case, because in this case the frequency characteristic is real. But you can see that I do this as a matter of habit, because oftentimes the frequency characteristic is complex, and I'm usually interested, not always, but oftentimes I'm interested in the amplitude frequency characteristic. So this is how I plot it. I label the axis, frequency index of the DFT, and the frequency characteristic. And now I can run this. Just to make it look slightly nicer, I will alter my y-axis. And now we can see it better. So this is my frequency characteristic, and you can see that it corresponds to this picture, except MATLAB is connecting these points with a straight line. Okay, now that I have that frequency characteristic, I can finally apply it to the spectrum of my signal. So I will take the spectrum of my signal and I will multiply it with that frequency characteristic, and I will get some altered spectrum, which I will denote as uppercase Y. Now that I have that altered spectrum, let's plot it. Again, I'm plotting the magnitude spectrum, and I will label the axis. And this is the plot of my altered spectrum. You can see that I have kept this part of the spectrum, I have kept that part of the spectrum, and this part of the spectrum is zeroed out. This part of the spectrum is zeroed out. And what happens on the right side of the spectrum is just the mirror image of what happens on the left side of the spectrum. So I have my signal filtered in the spectral domain, but of course I'm usually interested in what's going on in the time domain, so I need to take my game back into the time domain by computing the inverse Fourier transform. The IFFT is inverse fast Fourier transform, which corresponds to efficient implementation of the inverse discrete Fourier transform. So I have computed my signal in the time domain, and the only thing that is left to do is to plot it. And here you go. You can see that after I have applied filtering, I have kept those low frequencies and those higher frequencies are suppressed. You can immediately see that this doesn't work ideally, and we will talk on the next lecture how we can improve this. But just as a proof of concept, this works very nicely for us right now. Few important things to note. Do not forget about this rounding. Students tend to forget about this, then they end up with fractional k, and the rest of the stuff is just not going to work. At best, the MATLAB is going to complain. The worst case scenario is just the complete failure of the filtering. The next thing I want to point out is what happens when you screw up the symmetry in the spectrum. So let's, for example, delete this +1, in which case I do not have the correct symmetry in the spectrum, and now I will run the code. And this is what happens. This is my final signal. This is MATLAB trying to plot a complex signal. If I screw up the symmetry just by one sample, the resulting signal will be complex, and this craziness is what you get. And this is not what you want to get, so you need to be very cautious about the symmetry, about keeping the symmetry in the spectrum of the DFT. Okay, so this was a low-pass filter. What would I need to do to implement a high-pass filter? Well, for a high-pass filter, the frequency characteristic would need to be inverse to this one. It would need to be 0 for low frequencies, then it would need to jump up for high frequencies. And then we would have the mirror image. It would be high here and it would go to 0 here. So let's say that I want to keep all the frequencies about 300 Hertz. Now, this is how I recompute those 300 Hertz to the index of the DFT transform. Now I will generate the vector of zeros. And now I will need to set ones between some k and n minus k. So I will be setting to ones into the interval between k and the mirror image of n minus k. And of course, I need to remember that MATLAB has everything shifted by 1, so I need to add 1. And this is how I generate the frequency response for a high-pass filter. So let's run this. And here I have it. Here you have the frequency response for a high-pass filter. This is the filtered spectrum. You can see that I have suppressed low frequencies, I have kept high frequencies, and this is just a mirror image. And this is my resulting signal in the time domain. The low frequencies are being suppressed, and I keep the high frequencies. So this is how you implement a high-pass filter. Now, how would you implement a bandpass filter? Let's say that I would like to keep all the frequencies between 200 and 400 Hertz. So I would have two corner frequencies. I would start passing at 200 Hertz, and then I would stop passing at 400 Hertz. Now I need to recompute these frequencies to those indices of the DFT. This would be the first frequency, and this would be the second frequency. I will start with the frequency characteristic full of zeros, so no frequencies are being passed right now, and then I will add that I will be passing the frequencies between the indices k1 and k2. And of course I need to shift everything by 1 because of MATLAB. Now I need to keep symmetry, so I will need to do the same for the right half of the spectrum. And I need to shift this by 1 because MATLAB. Okay, let's run this. And here we have it. This is my frequency characteristic. You can see now that now it is a bandpass. I'm not passing low frequencies, I'm passing these frequencies, and again I'm not passing high frequencies, and this is just a mirror image. And this is my filtered spectrum, and this is my signal in the time domain. And you can see that I'm just passing a band of frequencies. Again, this is not ideal. You can see that the low frequencies and high frequencies are being a little bit passed as well, and I will show you how to improve this on the next lecture. Now we are just looking at the proof of concept. And just a quick reminder, let's see what happens if I screw up the symmetry. If I forget +1 here, this is what I get. This is not very good result. I need to keep the symmetry. Okay, so this was filtering in the spectral domain using a chirp signal. A little bit artificial, so let's take a look at something more practical. Let's apply the filtering in spectral domain to that ECG signal with power noise interference. On Moodle, you have this signal ecg.mat, which you can download into your computer. And then you can load it to MATLAB like this. Now I know that the sampling frequency in this case is 800 Hz. And also I know that in this signal I have a variable ECG where I have my electrocardiogram stored. So at first I will assign this to my signal X, and then I will plot it. And this is my electrocardiogram. If I zoom in, I can see that I have that power noise interference there. And of course, I want to get rid of that power noise interference. And for that, I will use that filtering in the spectral domain. And for that, I will use the same steps that I have used for the chirp signal. So at first, I will need to take this into the spectral domain by computing the discrete Fourier transform. Now that I have my spectrum, it is a good idea to take a look at it. And before I run this, I will label my axis. Here I go. And this is what I get. Here I have my ECG signal in the time domain, and this is its discrete Fourier transform spectrum. And remember, MATLAB gives me one period of the DFT spectrum with length which is equal to the length of that signal in samples. And also remember that this interval corresponds to the frequencies from 0 to the sampling frequency. In the middle, I would have half of the sampling frequency. Now, if I zoom in here, you will see what I showed you during the lecture. This part of the spectrum actually comes from ECG, and this spike actually corresponds to that power noise interference. That power noise interference is very close to a sine wave at the frequency of 50 Hz. And the spectrum of the sine wave are these two spikes. So to get rid of the power noise interference, I need to get rid of these two spikes. How can I do that? Well, I need to use the frequency characteristic. So let's generate the frequency characteristic. At first, I will define the frequencies between which I want to delete those spikes. So my first frequency will be 49 Hz. And my second frequency will be 51 Hz. And I want to delete everything which is in the frequency range between 49 and 51 Hz. So at first I need to recompute these frequencies which are in Hz to the indices of the DFT transform. So I need to recompute it to these indices. So let's do that. Remember the formula. It is the frequency in Hertz divided by the sampling frequency times the length of the signal. And I need to define that the length of the signal is my capital N. So this is the recomputation of the first frequency, and this goes for the second frequency. Now that I have these frequencies recomputed, I can construct my frequency characteristic. Except I shouldn't forget that these formulas can actually give me fractional numbers, so I need to round them. If I do not round them, I cannot use them as integer indices. Now that they are rounded, I can actually start generating that frequency characteristic. At first, I will generate it as ones. So now if I did not change anything else, every frequency would be passed. But I do not want to pass every frequency. I want not to pass anything that is between 49 and 51 Hz. Everything that is between these two indices. So I need to set this interval of the frequency response to 0. And of course, I must not forget that I'm in MATLAB, so I need to shift this by 1. And this would take care of this spike. This should delete this spike. But again, I need to remember that I work with symmetric spectra, so I also need to take care of this spike. I need to keep my frequency response symmetric. And do not forget MATLAB. Okay, and this generates my frequency characteristic. So let's take a look at it. Here you go. I will just scale the vertical axis so that you can see it better. And now it looks better. So you can see that the frequency characteristic is 1 almost everywhere except this narrow frequency band, which is centered around frequency which should correspond to 50 Hz. And you can see that this dip is nicely lined up with this spike in the frequency created by the power noise interference. And you have it for the left side of the spectrum and symmetrically for the right side of the spectrum. Now that I have my frequency response generated, I can apply it to my signal. So I will take the spectrum of my signal and multiply it with the frequency response. One thing I should point out, which I actually know and you had no way to find out by now, is that this signal is a column vector. I have generated my frequency response as a row vector. So for these two guys to fit in, I need to transpose my frequency characteristic. Now I will assign my altered spectrum into this variable uppercase y, and now that I have my altered spectrum, let's have a look at it. And here it is. Now you can see that these spikes, this one and this one, are no longer present in this spectrum. So I have removed that power noise interference, at least this part of power noise interference, from the spectrum, and I already have my filtered spectrum. But again, I'm not that interested in the spectrum. I would like to have my ECG in the time domain, so I need to take this back into the time domain by computing the inverse Fourier transform. This is it, and let's plot it. And this is my result. When I zoom in, I have my ECG with much less power noise interference than I had before. Well, you can see that I still have some interference left here. There is some noise. This does not have to be the power noise. That can be a different kind of noise. But you might have noticed that these two were not the only spikes in the spectrum that I have. I still have these smaller spikes. And you can see that they have survived the filtering and I still have them in the filtered spectrum. Well, these are just the third harmonics of the power noise interference. The power noise interference is not ideal sine wave, so it will not have only the fundamental, but it will also have the higher harmonics. And typically the most pronounced of those higher harmonics is the third harmonic. And if I want to do this thoroughly, I need to get rid of this third harmonic as well. So again, the fundamental is at 50 Hz, the third harmonic will be at 150 Hz. So what I need to do is to repeat this process. And now I will need to end the frequency band between 149 Hz and 151 Hz, recompute these frequencies to indices K1 and K2, and zero the frequency characteristic in this frequency band as well. And when I do that, I will end up with a frequency characteristic which looks like this, and you can see that now I have these two additional dips which corresponds to these spikes that correspond to that third harmonic of the power noise interference. And you can see that now in the spectrum even these spikes of the third harmonic, they are gone, and the ECG has slightly less noise in it. There is actually one more concept that is very nicely illustrated on this example. Let's take a look at this spectrum. You can very clearly see the first harmonic of the power noise interference. The spectrum of ECG is slightly more difficult to see. It's very small and you can see it only for low frequencies. You cannot see it for higher frequencies because it is so small that you cannot recognize it from zero. And this is a very common situation. At the spectrum, we can have very strong signals and very weak signals. And of course, we would like to see both at the same time. So to allow us to see this, we oftentimes use a logarithmic scale for vertical axis. So in MATLAB, instead of plot, you can use semi-log y, which will give a logarithmic scale on the vertical axis. It sometimes helps to scale this a little bit. And now I can very clearly see in the spectrum both strong parts, which is this first harmonic of the power noise interference, and these very weak parts, which is that ECG at very high frequencies. And for example, there is something which you were not able to see with linear scaling on the vertical axis. You were able to see the first harmonic of the power noise interference, you were able to see the fifth harmonic of the power noise interference, but only now you can see that actually that power noise interference had the fifth harmonic. So if you want to be thorough, you would need to remove the fifth harmonic as well. So do not forget about this. More often than not, you need to plot your spectra with logarithmic scale on the vertical axis. But normally we do not use this semi-log x. Normally we plotted it in decibels. So I will compute decadic logarithm of my spectrum multiplied by 20, and then I will plot it. And then I will get my spectrum. I assume that all of you know what decibels are. If you don't, just go ahead and Google it up. Okay, so this was filtering of ECG and removing the power noise using the filtering in the spectral domain. Now we will take a look at the filtering in time domain. We will do this partly theoretically and then we will dip into MATLAB to check how this works in practice. So the first example will be similar to the one that we ended the lecture with. I will give you the impulse response and I will ask you what will be the type of the filter this impulse response actually implements. So this is my impulse response. It is 1 for these values of the time index and otherwise it is 0. So first I need to plot my signal. This is my impulse response. Now if I want to find out what kind of filter this impulse response implements, I need to find out what is the frequency characteristic of that filter. And then I can find out by taking the Fourier transform of my impulse response. I'm doing that here. Now if I take the Fourier transform, the discrete time Fourier transform of this signal, I will get this. This number 1 will come here, for time index 0, and this number 1 will come here for time index 1. Now I need to alter this, so again I need to extract e to the minus j omega over 2, and what is left is this. Check it out. When I multiply this exponential with this exponential, I will get e to the 0, which is here, and when I multiply this exponential with this exponential, I get e to the minus j omega, which is here. Now this will give me a cosine, and this is my final frequency characteristic. Again, this is a complex function, and I'm mostly interested in the magnitude of it, in the amplitude frequency characteristic. So here I have the magnitude of that complex number, and this is what I get when I plot it. So what kind of filter is this? This is DTFT spectrum, so I need to take a look at this basic period from minus pi to pi, because the rest of it is just a repetition of this. And I can see that for zero frequency and for low frequencies, the signal is being passed, amplified a little bit, and it is suppressed for very high frequencies. So this is a sort of a low pass filter. Now let's go to MATLAB and check out if it really works. This is the code that I used for filtering in the spectral domain using the chirp signal. I will recycle this code, and I will keep this part where I generated my chirp signal, and I will get rid of the rest. Now I will define my impulse response. And now I need to compute, now to apply the filtering, I need to compute the convolution between my signal and my impulse response. In MATLAB, the convolution is computed like this. And this will give me my filtered signal. So let's take a look at it. I will first plot my original signal, and then I will plot the filtered signal. And this is the result. This is the original signal, and this is the filtered signal. And you can see that the high frequencies are being suppressed. And you can even see that the shape of this envelope corresponds to the shape of the frequency response that we computed. I can scale it like this so that you can see it better. So this impulse response actually does implement very rudimentary low-pass filter. Here I have another example with a different impulse response. And again, the question is, what will the filter with this impulse response do to the spectrum of my signal? Well, for that I need to find out the frequency characteristic, and that I will need to find out by taking the Fourier transform of my impulse response. In this case, the most convenient is the discrete time Fourier transform. So this is the general formula. Now I need to take a look at my signal, and I can see that there is a bunch of zeros that I do not need to sum, and there is another bunch of zeros that I do not need to sum. The only thing I need to sum is from 0 to 5. So I will get this formula. Here I have written it in general form for n non-zero lines. So here I have 6 non-zero lines, so for n I need to substitute 6. What I'm left with is this complex exponential, which is being multiplied by 1, by these ones. Now this is a finite geometric series, and on the previous lecture we actually did this, and I showed you what is the sum of a finite geometric series and how you can simplify this expression in this way to get this expression. We have already done that, just look it up on the previous exercise. Now this actually is the frequency response of a filter that has this impulse response. Again, at this time I'm interested to know what is the amplitude of the frequency response, so I do know how the amplitude of my signal will change at different frequencies, and this is the magnitude of this complex number. So this is the amplitude frequency response. When I plot this, I get this frequency characteristic. And now I need to interpret what type of frequency characteristic this is. I need to take a look, because this is a DT-FT spectrum, at the basic period from -pi to pi, and the rest of it is just repetition of this basic period. And in this basic period, I can see that low frequencies are being passed much more strongly than those higher frequencies. So this means that this is another type of a low pass filter. Okay, so let's check it out. Let's go to MATLAB, and now let's use this impulse response. And this is the result that I get. This is my original signal, and this is the result after filtering. Compare it with the frequency response, and you can see that this shape was created by this shape of the frequency characteristic. This shape got imprinted on the spectrum of my signal. Now there is one more thing to look at. This is the example that I have done at the end of the lecture. So here we have another computation for a different filter with this impulse response. And for this impulse response, we have found that this is actually a high-pass filter. So let's get into MATLAB and let's try it out. Now I will change my impulse response to this one, and I will run the code, and this is the result. Compare it to what we got in this example. So this part of the frequency characteristic shows me that it is a high-pass filter, and you can see that in the chirp signal, the low frequencies are being suppressed, and as I go to higher frequencies, they are being passed much more strongly. In the previous examples, MATLAB was computing the convolution for us. But what if somebody gave you this signal and this impulse response and asked you to compute their convolution by hand? These things have been known to happen, especially in your tests. So how would you go around it? Well, you just need to write down the definition formula for the convolution and evaluate it. Especially that simplification that I told you, which you can use when your impulse response has finite number of non-zero values. Then you can write the convolution like this. And actually this is how MATLAB is computing the convolution. There is just nothing magical about it. And you need to do the same. So let's take a look at what you need to do. Well, first you need to write down your sequences like this. You will take your first sequence and you write it like this. You will take the second sequence and you write it like this. Now let's take a look at what you need to do. You need to take your first sequence and then multiply it by the first element of the second sequence. I need to take my signal and multiply it with H0. Okay, I have that here. So I will take my signal multiplied by H0 and take this signal and multiply it by this number 2. And this is what I get. 1 times 2 is 2, 2 times 2 is 4, 2 times 3 is 6, and so on and so forth. This is what gives me this first element. Now the second element. I will take my signal, I have to delay it by one sample because of this, and then I'll multiply it by H1, by the second element of this second sequence. So I have that here. This is my signal delayed by one sample multiplied by H1. So this is my signal multiplied by -1. And you can see that -1 times 1 is -1. -1 times 2 is -2, and so on and so forth. And you can see that this sequence is delayed from this sequence by that one sample. And this just keeps repeating itself. Here I have my signal delayed by 2 samples and I multiply it by H2. Again, I have copied that here, my signal delayed by 2 samples multiplied by H2. So I take my signal and multiply it by H2. Very simple, this is 0. So the result is just zeros, and I must not forget to shift it by 2 samples against the original signal. And the last thing is that I will take my signal delayed by 3 samples and multiply it by this last element of this second sequence by h3. So I just multiply this signal by 1, I will get the same signal and I must shift it by 3. And this is the result. And the last thing that I need to do is to add everything together to implement these plus signs. So I will start adding. 2 plus nothing is 2. 4 plus minus 1 is 3. 6 plus minus 2 plus 0 is 4. And so on and so forth. This is how I add my numbers, and this is the result of the convolution. You're not sure about this? Well, we can check this in MATLAB. So in MATLAB, I will compute the convolution using the command conv. Here I will put my first sequence. And here I will put my second sequence. And this is my result. So check it out. Here I'm getting the result of the convolution, which is the same as I have computed here. So this is how you compute a convolution, discrete convolution by hand. So learn this. This may happen in your test. On previous slide, we took a look at the discrete convolution. Here we will take a look at the continuous time convolution. So for example, somebody will give you these two signals. You have signal x, which is given as the subtraction of these two unit step functions, and when you think about it and plot it, you will actually find out that it is just this pulse. And then you have this function y of t, and that is exponential, decreasing exponential multiplied by unit step. When you think about it, plot it, you will find out that it is this function. And now somebody might want to ask you to compute the convolution between these two signals. Why on earth would you need to compute the convolution between such two signals? Well, turns out that this function is actually the impulse response of this circuit. So if this is the input signal, the input voltage of this circuit, you can find out what the output voltage is, what the output signal is, by computing the convolution between the input signal and the impulse response. So how do we compute that convolution? Well, this is the definition integral, and all we need to do is just evaluate that integral. To be able to do that, we need to take a closer look what we have here. Well, the first important thing to note is that the independent variable, the integration variable here is tau. So when I'm going from minus infinity to plus infinity, I'm going through this interval with tau. T is just a constant for this integral. So for example, if I'm computing the convolution for time 5, then this t is just constant 5, and with this integration variable I'm running from minus infinity to plus infinity and computing that integral. The next thing to note is very simple. Here I have signal x, but it's not the signal x of t, but here I'm using x of tau. Well, that is just a different letter. Here is a little bit of change. Here I'm not using signal y of t or y of tau, but what I have here is y of t minus tau. So let's take a look what that does to my signal. I will start with the simplest case where t, my time, is actually 0. So when my t is 0, I will get that I have a function y of minus tau. And this minus actually causes this function y to flip. What do I mean? If this is my function y of tau and it looks like this, when I have y of minus tau, I will get function which is flipped. This is what I mean by flipping. Now what happens when the time is not 0? Well, then my function y of t minus tau will be shifted. So specific example, if t is minus 4, I will get this function, and that is actually plotted in here. This green function is function y of t minus tau for t is equal to minus 4. And you can actually see that it is this flipped function just shifted at the position of minus 4. Now when I evaluate the convolution, what I need to do is to multiply x of tau and y of t minus tau. Then when I multiply them, I need to integrate them from minus infinity to plus infinity. And to help you to visualize the multiplication, I have drawn these two functions in this plot simultaneously. So the blue function is x of tau and the green function is x of t minus tau. Now let's see what happens for t is equal to minus 4. I will have to multiply these two functions, but you can see that there are no overlapping non-zero values between these two functions. When I multiply them, I get zeros from minus infinity to plus infinity. So when then I integrate those zeros, I will just get 0. So in this case, for time is equal to minus 4, the convolution, which I will plot in here, will be just 0. Now let's take a look at what happens when I increase this time. Well, initially, not much changes. These two functions still do not have any overlapping non-zero values, so when I multiply them, I just get a bunch of zeros, and when I integrate a lot of zeros, I'll just get 0. So that is the result of a convolution for this time, and that will just keep being 0 until these two functions will start overlapping non-zero values, and that happens here. Now you can see that when I multiply these two functions, in this interval from 0 to t, I will be multiplying some non-zero values. Because, especially in this case, the function x of tau is 1. This is not in general, this is just in this case where I try to make things simpler. So in this case, when I multiply these non-zero values, I multiply these green values by 1, so the result are still these green values, just in this interval. So when I integrate in this interval, the result of the integral will be the area below this curve, this area. So as I increase time, you can see that the value of convolution increases. Now as I get to the point where time is equal to 2 and I pass that point, now these two functions will have overlapping non-zero values only in the interval from 0 to 2. So the convolution will be given by the area under this curve. And you can see that as I'm increasing the time, this area gets smaller and smaller, and you can see that the convolution gets smaller and smaller. Now I will restart this animation so that you can see how that convolution is being constructed. Okay, so now I have described how this integral works qualitatively. Now let's take a look how we can actually do those computations. So we will start with time which is less than 0. That is this case where the non-zero values of these two functions do not overlap. So when I multiply them, I just get zeros, and the result of the convolution is just 0. Now let's take a look at what happens for time in the interval from 0 to 2. That is this case where the non-zero values of these two functions overlap in the interval from 0 to t. So I need to integrate only from 0 to t. I need to evaluate this integral only from 0 to t. And that is what I have written here. I'm evaluating the definition integral only from 0 to t. Here I substitute for t of tau and y of t minus tau. What is t of tau? Well, t of tau is just 1 in this interval, so I will write 1. What is y of t minus tau? Well, that I will need to get from here, and I will need to substitute t minus tau for t. And that is what I have done here. And you can note that this unit step when you substitute t minus tau will be 1, so I don't have to write it here. And what I end up with is just a very simple integral which can be evaluated. You can crunch this and you will get this function. And this function is the convolution of x and y in this interval. Now let's take a look at the case where t is greater than 2. That is this case where the non-zero values of these two functions overlap in the interval from 0 to 2. So I need to evaluate this integral in the interval from 0 to 2. And that is what I'm doing here. So I'm computing this integral from 0 to 2. Here I need to substitute for x of tau and y of tau. It's very similar to what I have done here. So in this interval, x of tau is still 1 and y of tau is still the same as it was before. So the same substitution I have done here, I will be doing here. And now again, this is just a very simple integral. I can evaluate it, crunch it, and I will get this function. And this function is the convolution of x and y for t is greater than 2. So I can summarize these three cases and I can write that the convolution of x and y is 0 for negative time, it's this function for time in the interval between 0 and 2, and it's this function for t greater than 2. And this is how you can evaluate continuous time convolution. Basically what you need to do, you need to imagine and draw what these functions look like, especially when you flip and time shift this function. Then you need to realize what happens when you multiply these two functions, and then you need to integrate them. Often it happens that you need to break the integrations to several intervals in which the integration is actually simple. Now, one thing to point out, the discrete convolution, which we had previously, is something which is actually being computed when you implement the filter. When you want to filter, for example, your music, the discrete convolution can be something which MATLAB is going to be computing. But when you have a continuous time circuit, you can describe it using a convolution, but this circuit is not actually computing the convolution when it is taking this input voltage and creating this output voltage. So with the continuous time systems, the convolution is not really being computed within this system, but we can use it to describe what happens when we put some signal at the input of this system and we need to find out what is at the output of the system. And speaking about this circuit, at the beginning I told you that this is actually the impulse response of this circuit. So if we feed it this signal and we compute the convolution with this impulse response, we should be able to find out what is at the output of this circuit. So let's take a look whether we actually got something reasonable. I will move back this plot and move forward this time. And now let's take a look at it. If I feed this pulse into this circuit, what will happen? Well, for negative time, not much will happen. There will be just 0 voltage here. This capacitor will probably discharge sometime in the past, and I will have just some 0 voltage at the output. And that is what I can see here at the result of the convolution. Now, when this pulse comes, this voltage jumps to the value of 1 volt, and this capacitor starts to charge through this resistor, so this voltage will start to rise. And that is actually what you can see here. This is actually charging of that capacitor, and it will be charging all the way to the time 2 seconds when this voltage at the input drops, and then this voltage drops, and then the charge in this capacitor will start to flow through this resistor, and it will discharge again back to 0. And that is what you can see here. This is discharging capacitor back to 0. So this is how the convolution is connected to the real world time continuous systems.